Hey chemistry students, Mr. E here. I'm going to do another set of demos for you here today. This one I call is air pressure real. Now in the past I've done this as an inquiry thing in class where you would try to write and figure out what's going on, but that doesn't really work in this distance learning. So I'm just going to show you a series of demos and then I'm going to show you a drawing and an explanation about it. And it ties right in with the lessons that we've just been doing on the gas laws and the atmosphere. So here we go. Okay, so the first one I'm going to do here, you've already seen, and that's where I have the water in the flask with the screen over it. And then I turn it upside down, and the screen stays on the flask. I had talked earlier about this being an example of the cohesive property of water, where the water molecules are sticking to each other to make them too big to fit through the screen, and the adhesive property of water that makes the screen stick to the container. But there's another part working on it here as well. Do you really think just those little molecules of water could hold that screen up? I can shake it off of there, okay? But what's really going on is there's a little bit more right here. And let me show you in this drawing right here that what's going on there is when you have all the molecules in there of the water, and then they are sticking to each other. Well, we have air pressure all around in the room. So here I'm showing that through the cohesive and adhesive properties of water, the molecules stick to the screen, and then the screen is on the bottom of the flask. But what's really holding it on there is that all around, once that sticks on there, there's air pressure all around, and it's pushing back up on the screen, and it is holding it with more pressure than gravity can pull it off of there, helped along by the adhesive and cohesive properties of water. Okay, I'm going to do another one. And I forgot to say at the beginning right here, how do we know air pressure is real? As we're standing here, there's a column of air, we saw it in the atmospheres over us, hundreds of miles high, pushing down on everyone on the surface of the earth with about the same amount of pressure, and that is 14.7 pounds per square inch. Think about that. Every square inch of your skin right now has 15 pounds of pressure pushing on it. But you can't tell. So how do we know it's real, right? We are made to push back. We're not walking around as pancake people. Now I have a balloon that's in a water bottle right here, nothing else in there, maybe a little air. So I'm going to try to blow up that balloon. What do you think is going to happen? Okay, going to make a bottle look nice and red? Here we go. So you can see I got a little bit right there, right? But the balloon will not fill the bottle, okay? Why is that? Well, glad you asked. I have another little explanation of it right here, and that is that before I try to blow air into the bottle, I have the balloon in the bottle, but there's air in the bottle. There's air pressure also. I'm always showing there's air pressure all around, but there's air in the bottle. And so as soon as I blow into that balloon, I do manage to fill the balloon a little bit with some air molecules, but there aren't enough molecules in that balloon to push hard enough on the molecules in the bottle, and the air pressure in the bottle pushes back on the balloon and keeps me from inflating the balloon to the size of the bottle. And there's the explanation there. Now, just to let you know, I used to do a little bet with my students in class and tell you I would give you an A if I could blow the balloon up bigger than you. And I would take this bottle. Let's see what happens here. And I could usually blow that one up bigger than the other ones. Why is that? I cheated. I put a little air hole in it. So when I blow on the balloon, it forces air out of the bottle and allows the balloon to expand more. But I'm a teacher. I would never cheat, would I? This is not what you think it is. Stop laughing. This is a funnel with a tube on it used for scientific experiments, not for drinking things, okay? So all I have is I've got this little glass funnel and a hose on it. I can blow through and blow air through, okay? So I'm gonna put a ping pong ball in there. Now you predict, what's gonna happen when I blow through this tube as hard as I can? All right, think you know? You ready? Here we go. Okay, Try it again. I bet you thought that ping pong ball was going to go shooting up in the air, didn't you? I think you can see maybe it might be spinning. And that's all it's doing. Okay? Now, I'm going to suck on it. What's going to happen there? Well, I'm not going to get any air, right? So let's try that. Okay. So now I'm going to suck on it and turn the ping pong ball, turn it upside down. What's going to happen there? You're looking at that going, duh. Okay, you're sucking on it, Mr. E. Now, you ready for this one? I'm going to blow through this as hard as I can. Okay? And then I'm going to turn it upside down. Let's see what happens. Wait a minute. I am blowing through this. How that ping pong ball is supposed to go up in the air, isn't it? And then I turn it upside down. Once I run out of air, it falls back out again. Okay? That's a crazy one, isn't it? Why did that ping pong ball stay in that funnel when it's upside down? Well, that's a good answer. And that answer to that actually has a lot to do with why airplanes fly. And that's another thing. It's actually known as Bernoulli's principle. And so Bernoulli's principle says basically that, Bernoulli's principle says that when air goes around an object and it has to curve, it speeds up. And where air speeds up, its pressure is less than where it's going slower. So what happens is, in that funnel, when I have it this way, so if I have it this way facing up, when I blow into it, you think the ball is going to go up into the air, but it doesn't. The air escapes around it, and as it goes around it, it creates less air pressure here than up above, and the air pressure in the air keeps that ball stuck down in the funnel. Now, when I'm blowing through it and it's doing that, remember, I have less air pressure coming around it here and more air pressure this way, and when I turn it upside down, that difference in pressure is enough that the air pressure holds that ball in there stronger with more force than gravity. So it's kind of an interesting thing. Once I start running out of air and the air slows down, then the ball falls out. So that's Bernoulli's principle right there, which is, I think, quite interesting. Next what I'm going to do here, I don't know if these guys are ready or not. So I think what I'll do is I'm going to turn our attention over here to this vacuum chamber. And I'll come back and see if I can get the pop cans hot enough. They should be on. Here we go. Okay, so this is a vacuum chamber. In this chamber right here, when I turn it on, when I put this on top, it takes air out of this container right here, okay? So what I have in here right now is I just have 3 little water balloons, is what they are, in different, blown up to different sizes right here. And so we've been talking about air pressure, and we were talking about pressure of gases and volume and pressure going back and forth. So right now, when I have a balloon that's sitting here, there are gas molecules, as you recall, in the balloon zipping around, hitting against the sides of the wall of the balloon. They would allow the balloon to get bigger if they could, but the air pressure in the environment is pushing back down on the balloon, and it will not allow those molecules to make that balloon get any bigger than that. But let's take a look at what happens when I take the air out of the chamber. Let's take a look at those balloons. Okay, so here we go. Remember, I'm not putting any more gas into the balloons. It's the same amount in there. The chamber doesn't. There we go. So the little one's going up right there. So how'd you do? Made my camera person jump a little bit, right? Now watch what happens when I let the air back in. Dancing balloon pieces. Okay, but that doesn't just have to happen with balloons. This is sort of an interesting one right here, okay? Now, you might have done something like this in the microwave, but it's a little bit different right here, all right? So here we have some marshmallows right here, just some regular Fruit Club marshmallows. There were some we used to buy, and they said they were jet puffed. So what the heck does that mean? What makes a marshmallow fluffy? I don't know, marshmallows are interesting. Nothing natural added, I don't think. But really what you have sugar. and a few other ingredients. But let's take a look at those marshmallows now. I like them big on my s'mores. There we go. Ooh, I love those big marshmallows. What the heck is going on there? Yeah! Ooh, that is going to be tasty. All right, I can hardly wait to get my hands on it. Here we go. Gonna get me a nice big marshmallow right there. Yeah. Oh man, I'm gonna make a mini marshmallow. Okay, and I could do that again, and guess what? It would get a little bit smaller. All right. So no, this is not how they make mini marshmallows at the factory. Okay, that would take a long time. So what the heck is going on? It's the same principle with the balloon and with the marshmallow. So come on over here and take another look at my diagram right here. This is what I did in class a couple years ago, is the students actually had to draw these all out, explaining what's going on. And so here, this is the one with the balloons in here, and again, the balloon has a certain amount of air molecules in it. And when I put it in the vacuum chamber, there's air in there as well, and so it's pushing back on the balloon. But once I turn the vacuum chamber on, it starts taking air molecules out of the chamber. Those gas molecules in the balloon have less pressure on them. They are able to bounce against the sides of the balloon with more effect, and they make the balloon get bigger. The same thing with the marshmallow. Marshmallows are mostly air. Not mostly, but there's a lot of air inside of them. So when I put the marshmallow in there, it's sitting there and it's got all these air pockets trapped in there amongst all the sugar molecules. Well, once I take the air out of the chamber, that air in there has more pressure than the pressure around outside of it, and the air molecules actually move out of the balloon. Well, move out of the marshmallow. And as they move out of the marshmallow gets bigger. But then they're gone from the inside, and as soon as I let the air back in, the marshmallow shrinks, because now where the air was, there's a lot of empty space, and it shrinks right down again. So there's that one. The next one I'm going to do here is I have some cans, empty cans here, sitting on some heat, and I've heated them up inside. And now I'm just going to take this can off and I'm going to put it in here. Oh, I know, that was all done with cameras, wasn't it? Actually, I squeezed that around as fast as you see. I'm squeezing it around like that, squishing it. No. What the heck's going on there? How did that can collapse? Let's see if we can do it again. And if you want to see, there's a video of a railroad car doing this. Here we go. And to tell you the truth, I did this once when I was getting my master's degree up at Western, and we were in Red Square up there with the fountain in the summertime, and we were screwing around in my class. We actually had dry ice, and we were doing dry ice bombs in the waste baskets, but we heated up a 55-gallon drum with a weed burner and pushed it into the fountain, and 15 minutes later, this big 55-gallon drum did exactly that. I'll tell you, that was impressive. Okay. So what do you think? So this last one wasn't hot enough, but we'll see if it works. I've got 4 here, so let's try this one too. I don't think this one's gonna go. Nope. That one I just put on and wasn't hot enough. So you can see it actually doesn't work if the can isn't hot. Well, what's the heat got to do with it? Well, I'm so glad you asked. So on this one here, on the cans, they're all, you can see, they're almost all the same thing. And what happens is, as we learned, when you heat a gas, it gets excited and it expands. So when the cans are sitting on the heat, the air inside is getting heated and it expands and it goes out of the can into the atmosphere. Well, as soon as I take the can off the heat and I turn it upside down in the water, 2 things happen. 1, the water seals it so air cannot go in or out. And 2, the water cools it very quickly so the air shrinks and that can is crushed simply from air pressure. So there's a little force to that air pressure right there. Okay, and the last one I call egg in the bottle. Okay, and this one's gonna stink up my house a little bit, but that's okay. So here's what I have. I have some Kleenex here that I'm gonna actually light on fire and put in this milk bottle. You don't see milk bottles like this very much anymore. The old milk bottle, okay? I have here a peeled hard-boiled egg, okay? So that's what I have, that's what I'm gonna do. Hopefully it'll work. So I'm gonna make a little cord out of this. Let's see, maybe I'll do it like that. Here we go. Hey, did you see that video where Mr. E burned down his house? That's so cool. Best video we've ever had. Okay, so I'm gonna drop that in there. Okay, now I'm gonna put the egg on. How you like that? Yes, sir. What the heck? How'd that egg get in there? Okay, we'll do it again. Here we are. I'm heating up this Kleenex and sticking it in this milk carton. I'm gonna put this boiled egg on top. Yeah, it makes me jump every time. I love that. Okay, so here's my explanation here on that one. I better give you that last explanation. I think you figured it out. It's probably pretty much the same as it's been every time. What's going on right there is when and you have to hard boil the egg, and you have to peel the egg. It won't go in if you don't peel it. So what happens is I put the paper in there. The paper in there heats the air. The air expands and rushes out of the bottle. When I put the egg on, the egg kind of bounces around a little bit as the air is going by, but then as the fire cools down, the egg sits on the bottle and seals it. And when the fire goes out, the air cools, there's less air inside than out, and the atmospheric pressure shoves that egg down into the bottle. So there you go. And there are my demos right there. And so, what do you think? Is air pressure real? Thank you very much, and I'll see you again, chemistry class.